Hey there, welcome to video 14. Today we're going to continue our discussion of transistor parameters and active region models, and we're going to look at the collector curves a little bit more as well. To start with a bit of review, we've been talking about NPN transistors, and this is the active region model we've been using. We could adapt it to PNP transistors just by reversing all the polarities of the currents and voltages. Everything else would work the same. We're going to stick with NPNs primarily from here out because in real life most circuits use NPN transistors way more than PNPs. So with that in mind, unless there's some really compelling reason where we absolutely have to use a PNP, we're going to stick with NPNs. All right, remember from previous discussions that beta is defined as the ratio of collector current to base current. There's another important parameter for transistors called alpha. That's the ratio of collector current to emitter current. Most of the time, we're going to be using alpha in our design and analysis examples, but occasionally alpha is useful too. Beta and alpha can be written in terms of one another, as seen in these equations down here. Beta equals alpha over 1 minus alpha, and alpha equals beta over beta plus 1. All right, before we move on, in order to get a little better handle on what alpha and beta really mean, let's do a few calculations. All right, so let's use our good old friend, the 2N3904 transistor, as our guinea pig. All right, remember beta for the 2N3904 ranges from a low of about 50 to maybe a high of 300. Typically, we assume it's about 100, but it could be anywhere in this range. So let's say we grab one at random and it has a beta of 50. What's the corresponding alpha? Well, remember alpha equals beta over beta plus 1. So it's 50 divided by 51, and that gives us a beta of about 0.98. All right, now if we grab another random 2N3904 and it happens to have a beta of 300, the corresponding alpha is beta over beta plus 1, 300 divided by 301, and that gives us an alpha of about 0.997. All right, not too much difference. Just for the sake of completeness, let's assume we have our typical beta of 100. That corresponds to an alpha of 100 over 101, which is 0.99. All right, so the main takeaway here is that even though the beta varied over a pretty wide range from 50 to 300, the alpha only varied from 0.98 to 0.997, and in all cases it was pretty close to 1. So with that in mind, a reasonable approximation that we can use is alpha is about equal to 1. And that's equivalent to assuming that emitter current is about the same as collector current. We've used that approximation previously. It's equivalent to saying alpha is about equal to 1. All right, so let's take this ideal model down here, okay, to represent a transistor, and let's develop some collector characteristic curves using this ideal transistor model. All right, we're assuming this dependent current source has infinite internal resistance, and this is an ideal diode with no barrier potential, just a perfect diode. All right, if we developed collector curves for this model, this is what we'd get. All right, because the diode has no barrier potential, we have 0 for our VCE sat. That is, the collector to emitter saturation voltage is 0. And because this current source has infinite internal resistance, these collector characteristic curves are perfectly horizontal. That corresponds to infinite resistance in this current source. And another thing that isn't apparent yet is that this is a perfectly linear model, so the spacing between these curves is perfectly uniform as well for equal steps in base current. All right, that's a good enough approximation for a lot of applications, but we might want to get a little bit more accurate than that, and we're going to take a look at that in a second. But before we go to the next slide, remember we've defined beta as collector current over base current. Now technically this is beta DC. Okay, it's defined only for DC currents and voltages in the circuit. We could also have an AC beta, which is a frequency dependent beta, but for audio frequencies the difference between beta DC and beta AC is negligible, and we're just going to assume they're the same thing and just call it plain old beta. All right, and another thing you may have heard of is hybrid parameters. This is just another way of defining the behavioral model for the transistor. The hybrid parameter H sub capital Fe is the same as beta DC, and H sub lowercase fe is beta AC. We're not going to worry about hybrid parameters, but you may run into that notation, and this is the interpretation. All right, so let's get back to these curves and make them a little bit more realistic. And here we go. All right, for a real or pretty real transistor, these are the kind of curves we're actually going to see. Now notice we do have a VCE sat of around 0.2 volts. That's about where these curves level off. And the curves are not perfectly horizontal, but they tilt up to the right a little bit. The higher you go, the more tilt you get. That's not apparent here, but it will be in the next slide. But to account for this tilting of these curves, we include a resistance in parallel with this current source. That represents the internal resistance of this source. We're just bringing it outside so we can look at it. All right, we designate it as lowercase italic r sub o, little ro. Dynamic quantities that change with operating point that are internal to the transistor are usually represented with a lowercase italic letter. So hence little r sub o. All right, now if we had these curves in front of us on a curve tracer and this was the values we got, we'd see that for a change of 2 volts in VCE, we got a resulting change of 100 microamps in collector current. So we could determine the effective resistance of this current source RO by using delta VCE 2 volts divided by delta IC 100 microamps, and that gives us a little RO of 20 k ohms for this particular transistor. That's a fairly realistic value for a transistor like a 2N3904. All right, now the tilting of these curves, as I said before, as we go up, the tilt gets more and more pronounced. Okay, they get steeper and steeper. If we exaggerate that a little bit, we come down here, we get this. All right, notice that if I project the collector curves back, they intersect the VCE axis at a common point back here, and that is called the early voltage for the transistor. It's designated V sub A. And this whole thing that we're looking at here is called the early effect. All right, it's named after James Early, who was a pioneer in transistor development that quantified this stuff. And if we divide the early voltage by the approximate quiescent collector current that we've got, and remember I'm exaggerating these curves, we can plug it into this formula and get a good estimate of the internal resistance of the collector current source. So it's V sub A, the early voltage, as a positive number divided by ICQ that you establish at your Q point. All right, a lot of times we don't need to go to this level of accuracy, but if we do, hey, we know how to calculate it. Now, V sub A is not usually given on transistor data sheets, so if you want to find out what that is, you would have to calculate it based on collector curves given in the data sheets. But in any case, here it is, and we're going to use this stuff off and on through the remainder of our transistor analysis and design problems. So hopefully this was a little bit interesting and useful, and I will see you in the next video.